Welcome to the fourth Compass lecture of the semester. My name is Donnie. I'm one of the coordinators of the Compass lecture this semester. I want to introduce this week's speaker, Cooper.
It's like Jacobus, like Jacobia.
Cooper Jacobus. He's an undergrad student here at Cal studying astrophysics and philosophy. He's a student researcher at UC Berkeley's Department of Astronomy and LBNL. The Center for Computational Cosmology. He's fascinated with a range of topics from cosmology and the birth of the universe, translating physical phenomena into algorithms, and understanding the nature of intelligence and computation. Cooper's also passionate about teaching and has taught and has served for 2 years as an instructor for the Intro to Astronomy class, and as well as mentored other undergraduates who are looking to get involved in cosmology research. So let's welcome today's speaker, Cooper.
I thank you guys all for being here. I'm really excited and honored to have this opportunity to talk to all of you. And I hope that I can give you a very general introduction to what is research like in the space of cosmology, what is research like in the space of machine learning applications to physics. And I'm trying to paint a picture in very broad strokes for all of you as best I can in the time that I'm given. So I'm just going to get right into it. So what you're looking at here is a simulation which was done on a giant supercomputer of the formation of structure in the universe. These bright points which are emerging, these little spiral clouds of gas and dust, are the beginnings of what will later be galaxies. These are baby galaxies emerging. But in between them, you can see all of this fascinating turbulent structure, these webs of gas between galaxies. And this will be the focus of my talk today. Will be what is called the cosmic web, which you're looking at here, the structure of the matter in the universe between galaxies, not just in individual galaxies, but what is going on in space, in the space between galaxies, and what can we learn about the shape of the universe from this. I'm going to break this up into a couple of different parts, trying to paint maybe 3 distinct pictures. What was that cosmic web? To give you a brief introduction of what is our modern picture of cosmology, the history of the universe, and then why that cosmology and history of the universe would cause structural life forms to form. And then part 2, I'll talk about how do we study this thing? What can we learn about the universe by studying this thing? And finally, talking about my own research personally, applying machine learning to simulations like this to accelerate. So I'll get right into part 1. What the hell is the cosmic web? And to do this, we have to talk about this entire history of cosmology, what is going on in our universe. But the cosmic web is going to be just a catch-all name for the structure of the universe. Each of these individual bright points here are going to be new forming galaxies, but there's all of this complex structure, this web-like structure of this diffuse dispersed gas in between these formations of galaxy clusters. This is what we mean when we say the cosmic web. But now we want to talk about how did this get here? And to do that, we have to talk about the expanding universe. So I hope that you're familiar maybe with this kind of picture of space-time, this kind of picture of general relativity. This is a very common thing that appears all over media, social media, whatever. Einstein tells us that space and time are not a constant playing field in which things move around. They're actually dynamic, and they can bend and change due to the presence of masses. In fact, we see in pictures like this that gravity is a consequence of the bending of space-time. If you have a massive object, it curves space-time around it so that things moving in its vicinity, curve in its direction. I'm actually really partial to this picture, which is just a rewriting of what we saw before, but it's in 3 dimensions now, where you have some massive object is pulling space-time towards itself due to its mass. Its mass is causing an influence in the shape of the universe around it. Sweet. So this is, I hope, a familiar picture to you, even if you haven't taken like a class on general relativity. You probably have been exposed to these ideas in general, but we can expand upon them quite literally. in this picture, even though space is curving and moving and shifting, overall, the size of this cube is pretty constant throughout, right? It's not changing volume very much. But what would happen if we just took this cube, this space-time, and stretched it out? We know that we can do this. The math allows for it, at the very least. The math doesn't say anything about, what is the overall shape of space-time as time progresses. Does it have to stay relatively fixed, like in this movie, or can we play fast and loose with the size of space itself? And it turns out, by doing, very precise experiments, we can find out that space itself is expanding over time. Since the beginning of the universe, space-time itself has been getting bigger. Getting bigger into what is a profound question we can talk about maybe later, but space-time, it seems like, is getting much, much bigger. Things in the early universe seem to be much closer together on average than they are now. And we can paint an interesting picture by doing experiments, thinking about, well, what does it mean if the universe is expanding? How would we measure that? You can think of all of the galaxies in the universe, all of the other stuff out there, as being like on the surface of a balloon that you're blowing air into. And if you look at one point on the balloon nearby, you would see it getting further away from you. But if you look at a point which is even further than that, it would seem like it's moving further away faster. The further away you look on the surface of the balloon, the faster that thing seems to be moving away from you, if we're blowing air into the balloon. And if we check this, if we look at faraway galaxies and then measure their velocity relative to us, we see this very convincing trend. Here's another picture of this. Galaxies which are further away ought to be moving away faster if the universe is expanding. If we measure this, we actually see this trend line. We see the further we look away, distance measured in megaparsecs is some unit of distance, and velocity measured in kilometers per second, there seems to be this kind of proportional relationship. The further we get away from the Milky Way, the faster that thing seems to be moving away from the Milky Way. And there's no center of this expansion, just like there's no center of the balloon. Every point on the balloon seems to be moving away from every other point. This is consistent with this expanding universe notion. But what the hell does this have to do with the cosmic web? How does this expansion shape that crazy, intricate structure I showed you before? Well, it's all about the conflict between this expansion pressure and the infall of gravity. Gravity, as you're well aware, tries to pull everything together. You have some big galaxy, everything nearby is going to be attracted towards that galaxy. So what happens if you contrast the inward collapse due to gravity with an outward global expansion like what we're seeing? Okay, well, here's just another picture of that. All of the individual stuff nearby are going to be falling in towards these galaxies, but the space itself is expanding. So the galaxies are being pulled away from one another and might in fact stretch out the stuff that's in between. Okay. I'm gonna switch to showing you a clip from a YouTube video that I think really demonstrates this phenomenon.
Leg. Love videos of this. It's absolutely what cameras like this before. So slow down. Oh, straight through. I feel like that egg got shattered more. Maybe it's just slightly more frontal.
So here we have some kind of global expansion.
I don't know, maybe.
Which is exploding.
And then
But look, if we look at individual points,
yeah, the overpressure of the egg. That's what
surface.
Is the egg from
So we have this kind of analogy
to
the expansion.
Yeah,
Universe
fan like
structure.
a yolk on
There's a
it.
global expansion.
There you go. That's the egg just on my leg.
If you look closely,
You can't get enough to say.
Play that clip again. Go here. Come good. If you look closely, you will see these interesting web-like spindle structures emerging. There'll be certain nodes, and then between those nodes are little spindly connections of egg.
I wonder if that was visible on the frontal, because it is casting a shadow.
This is
You feel like the
very
air
much
is like a
analogous
different
to
density,
the
the
structure
light
that
is
we
like,
emerge in the universe.
yeah, it's like fractured. Then
Go back to the slides. So I hope you'll agree that this looks similar to the structure that emerged in the egg. And the reason is effectively the same. Even though, this is only like a first order approximation, gravity and surface tension don't really behave the same. But in general, it's a really good analogy because we have this local attraction, the egg goop is going to try to clump up with its neighbors, whereas overall the egg is expanding. Just like the universe, the matter due to gravity is going to try to clump up with its neighbors, but overall is expanding, which will rip it apart into these very interesting and complex web-like structures, just like the egg. So, using this information, and this story that we've told about how the universe has gotten to look this way, how can we learn about the cosmos itself by studying the structure? So first we might talk about how we map these, how we actually take pictures of this stuff. I'm sure you've seen just like this is the Hubble deep field and Webb deep field. You know, where's the cosmic web here? I'm supposed to be looking out into the universe at these distant galaxies. I don't see any of these, web-like structures I was talking about just a second ago. Well, we have to look in 3D. Well, this is just the 2D projection. If we make a map of galaxies, here I've plotted, their angle in the sky and then their distance away from us. You can begin to see these spindle structures emerge. This was data from, now a long time ago, and we had goes much deeper, further into the universe, mapping galaxies based on their distance from us and where they are in the sky. I'll just let this video play out because I think it's very cool. Each one of these bright points represents some galaxy or small satellite galaxy out in the universe, some distance away from us. And you could see in the earlier picture that when you zoomed all the way out, you could see the spindle structure, the web structure emerge. Lovely. So we've made this map. What the hell is the map good for? And can we even look further back in time? The further away we look, the dimmer these galaxies are, the harder they are to see. If we want to look further out into the universe, and therefore further back in time, we have to use some other methods. Fortunately, there's other options available to us. We can look at the shadows by this gas. This gas is made of hydrogen and helium and everyday stuff. And so it's going to absorb certain wavelengths of light. Just like hydrogen clouds, like here on Earth, will absorb certain wavelengths of light. If there's light coming from the distant universe that passes through these clouds, it will be absorbed. And we can check for those shadows. So we're looking here at the spectra of different quasars, way in the early universe, as the light traveling from those very bright objects passes through clouds on its way to us. Light is going to be absorbed, and we can use the spectra of these quasars to map the universe. The light coming from the quasars should be approximately uniform. It should be this continuous distribution, but we see all of these dips. And everywhere that there's a dip, there's a cloud of gas that it's passed through, that's absorbed some of the light. Awesome. If we collect lots and lots of these quasar spectra from objects way in the distant universe, we can piece together a map of the shadows, something that looks something like this. And you can see from this image, the structure emerges once again. Looking even way back in time, we can see, oh, there's these cosmic web structures, even in the very distant universe. But what do we do with all of this? Well, this is just one part of the picture. These maps alone don't tell us very much, but we want to measure things like how fast is the universe expanding or how much matter is there. These are things which would affect the shape of the structure. If the universe was expanding very quickly, well, then all of these structures would get ripped apart a lot faster. And the separation between one clump of galaxies and another would be very great. If there were a lot more matter in the universe than there was, things would clump up together a lot more, or much like denser, tighter balls than a diffuse clouds if they were less. So somehow we have to compare what we observe to some kind of theoretical model to gain an understanding of what are the actual parameters of our universe. The parameters being how much matter is there, and what is the rate of expansion of the universe, or what is the overall curvature of space-time. These are things that we can learn by comparing these maps to simulations of some kind. So, general overview of how we make the simulations. There's the other part of this picture. We have some understanding of what the universe looked like very near the very beginning. The cosmic microwave background tells us what the universe was like just 400,000 years after the Big Bang. And we can make a computer simulation starting from that moment and based off physics that we already know and understand, physics of gravity, physics of fluid mechanics, and evolve the universe forward from there according to some, assumptions about what the parameters for the expansion of the universe and the amount of matter are, and see what we get. Make a bunch of simulations, some where the universe is expanding very quickly, and there's a lot of matter, some where the universe is expanding very slowly, with not as much matter. And compare those simulations to the data that we take in real life to try to get these constraints. Sweet. So how the hell do we do these simulations? That's what I'm going to talk about now. Gravity is pretty easy. You can make a simulation of structure formation from gravity by just plopping a bunch of particles in some imaginary grid and saying, well, this particle has this mass, this particle has this mass, they're this close to each other, so there's this force between them, and they're going to attract by this amount. Stepping forward in time, just very slowly and say, like, the particles are here now, then, a few years later, they're here, a few years after that, they're here, and see them attract towards one another. The other thing that we have to include in a simulation like this is expansion, but this is straightforward enough. We just have to take the grid that we've put everything on and stretch it out as we go along according to whatever our expansion rate is. And the final ingredient in a simulation like this are the initial conditions. We have to also start our simulation somehow, because the result that we're going to get is going to be very much dependent on how we start out. If we start out with lots and lots of clumps already, then we're going to end up with lots of clumps. They're just going to stay like that. So we have to base our initial conditions off of some kind of observations we've made, these coming from the cosmic microwave background. The CMB tells us what were the fluctuations in the density of the universe at this particular moment. So these hot regions might be slightly denser, there might be slightly more stuff in the red spaces and slightly less stuff, ever so slightly less in the blue spaces. But these perturbations in density are enough to be the seeds of structure formation. So if we start a simulation of gravity with just very little fluctuations in overdensity and underdensity, and let the simulation run, they're going to attract and form these clumps and form these very recognizable structures of web emerges. Maybe I'll play that one more time so that you can really notice that at the very beginning, it's almost uniform with very small fluctuations whose amplitude has been set by measurements of the CMB. But those small fluctuations are enough to be the seeds of the formation of the structure. A region which is just ever so slightly denser than its neighbors will attract matter and form these clumps, form these galaxies and clusters. Sweet. But what about all that crazy fluid mechanics from before? In that first movie I showed you, it wasn't just gravity. There was all of this crazy turbulence going on. How do we simulate that? Well, we can, here, let me show the video again so you can watch. If you look closely at regions like this, it's not just collapsing onto itself. It has temperature, it has angular momentum, it has all of this extra stuff going on, all of this crazy turbulence, all of this chaotic dynamics. We have to simulate this somehow as well if we want to get something that looks realistic. So how do we go about doing that? Well, we can kind of create a grid. For every point in space, we keep track of what's the density, what's the temperature, what's the velocity, how are things moving and changing. The same way that we would keep track of like the temperature in this room or the density in this room, rather than tracking each individual particle, we can keep track of the average throughout different regions of space. This is called fluid simulation on a linear grid. So each individual pixel here, we have a different density, we have a different velocity, and we have a different temperature. And we have some kind of equations that tell us how they should change based on the values of their neighbors. Fluids have some kind of viscosity. And they move. If they have a velocity at one point in space and there's a density here, at some time later, that density should be transported to the direction it was going. So if I start with a bunch of density here and it's moving that way, well then sometime later the density should be transported in that direction. But also there's this viscosity you have to take into account. The density might diffuse throughout space, and the velocity might diffuse throughout space. Like if you, I don't know, make a splash in a pond, you start with all of the water just right here moving, and then none of the water next to it moving. But a few seconds later, all of the water will be moving in that direction. The fluid is affected by the motion of its neighbors. So if you start with some kind of velocity or something like that, eventually sometime later, it will align with its neighbors, spread out. But now that we're doing fluid simulation like this, the accuracy of these simulations is going to depend on how small we make those little boxes. Okay, that makes sense. If I make those boxes really, really big, I won't capture the dynamics, the interesting chaotic turbulence that goes on at small scales. It'll just be, washed out, blurred away. I'll show you an example of that. Here's a really expensive simulation. This is a huge region of space, because remember, each one of these little bright points is a cluster of galaxies. We're talking about an enormous amount of space here. But to do a simulation as huge as this costs a ton of money, costs a lot of supercomputer time, which costs power, and power costs money if you've ever paid your electric bill. But we can do a much cheaper version of this by just making all of the individual pixels bigger. But that ends up looking like this. I think you'll agree with me that this, seems a lot less useful. It tells a much less compelling story about where these structures are. And if you remember that how we're going to constrain the cosmological parameters at the end depends on, how well our simulated maps match our real maps. And these two simulations don't even match each other. So you might guess that we can't use a simulation like this to do precision science with. Even though it's, telling us some kind of interesting story, it's not telling us the right story. It's not telling us what the universe with this kind of physics would actually look like. So this is a really, really big problem for us. We can do a cheap simulation that's useless, or we can do a really expensive simulation. The thing is, doing a really expensive simulation on the scales that we would need to do the kind of science that's coming in the next decades would cost the amount of power that a small town consumes in a year for each simulation. And remember that we have to do maybe hundreds of them or thousands of them to do one for this condition, one for this condition, one for this condition, testing lots of possibilities to see which corresponds best with reality. So this is entirely too expensive a program for us to run. So we have to find some way to get around this. Sweet. Applications of machine learning. So I wouldn't have presented this problem for you if I couldn't have suggested to you some way that we can solve it. And this is now where I'll begin to talk about my own research. So how do we begin to try to solve this problem? So just to state the problem in a better way, since we can't do a really big simulation that's at really good resolution, we can only do a really big simulation at that low resolution. We want to somehow train a machine learning algorithm to take in the low resolution output and make it look better. Here we have, I should get rid of this thing again. Here we have the low and high resolution simulations. We want to somehow translate between them. So we can kind of cheat the system a little bit by running the low resolution simulation and then applying some kind of machine learning correction factor to make it look better, to make it look like the structures are less blurry, to make it look like it would match the actual reality that we would see better. So somehow we want to train a machine learning algorithm to translate between these two things so that we can make a really, really big simulation that's still as though it's at high resolution without spending the sign of supercomputer time to make that actually the traditional way. To do this, we have to run a little bit of these high resolution simulations, but small ones that take up not much space, only cover a very small volume, and then pair them with low resolution simulations so that we can have training data to translate between low resolution and high resolution. And if we feel confident that we can do that for this small volume, we can run a much, much bigger volume at low resolution and then feed it through our machine learning algorithm to do this. So I'll give you a little bit of a picture of What does that mean? And what does our algorithm look like to do this? We're going to use what's called a convolutional neural network. This is a little animation of what a convolution is. It's translating from one picture to another picture. On the bottom, we have, some kind of array of pixels. Each of these pixels you could imagine has a different value for something like density or temperature or color or whatever. And we're applying this like what's called a kernel, which is like a mathematical operation, like a matrix multiplication, or more like a dot product, where this little 3x3 box has values learned. And at each point in space, it goes through and it multiplies the values in the 3x3 box to the values of the space that it's on top of, and then returns the answer to that as the value of the pixel in the image on top. This allows us to do what's called feature mapping, where different filters, different kernels can be convolved with the image, and will produce a different map of what is in the image. One kernel might tell you, okay, here's where all of the vertical lines are. One kernel might tell you, here's where all of the horizontal lines, or the diagonal lines, or the dots, or whatever are. So each of these filters will tell us which things are in which places in the picture, and decompose our picture into a map of where things are. Now we can design an algorithm which decomposes that low resolution picture into a feature map, encodes it into a map of here's a galaxy cluster, here's a filament, here's another galaxy cluster, here's another filament, each of them corresponding to a different shape, and then feed that into a generator which takes in the map of here's a filament, here's a galaxy cluster, etc., and turns it into what it would look like if it were a higher resolution simulation. Sweet. So we have this machine learning algorithm which receives as input the low resolution data. So I've called it in this slide the coarse data, the density, the temperature, and the velocity of this gas at every region in space, decomposes it into a map of where everything is, and then generates a new map which is higher resolution, but has all of the same features in the same place. Sweet. So each of these filters, each of the things that makes one of those feature maps is learned like a machine learning algorithm. We've trained it on the data so that we say, we're just going to initialize all of these filters randomly and see how well they do at reconstructing our training data. And then we're going to try to make them better. So take their derivative with respect to some kind of score, and then step in the direction to make the error, not as bad. And eventually we're going to end up with something which encodes our data very well, and then is able to reconstruct it in some way that looks a lot like the real high resolution simulations. So let's see, what does that end up looking like? Well, okay, the two columns on either end, you're already familiar with. They're the low resolution and the high resolution simulation. But the column in the middle is actually the one which is reconstructed by our machine learning model. So we take in as input this side, and then we reconstruct it so it looks a lot better. I hope that you're able to see, this is why I like closed all the windows. I hope that you're able to tell that this middle column looks a lot more like the high resolution data than the low resolution input does. By decomposing this image into a map of all of the features and then reconstructing it from that map, we're able to improve the effective resolution by a lot. All of these features look a lot better. Where before there were diffuse clouds, now we have very thin, very well resolved features. Cool. But, yeah. Yes, we did. Yeah. Yes. Oh, sorry for the zoom. So this is a sample from actually our testing data, but which is kind of like our training data. We've no, but we trained on images very much like them. So you can imagine that we did, and the images that we do train on look a lot better. Effectively, we have a set of training data, a set of pairs of low resolution and high resolution simulations, and we train our machine learning algorithm to translate between them. We also keep a separate set, a smaller set of data of pairs of low resolution and high resolution simulations to test our machine learning model on, to make sure that we're not overfitting. In other words, we could have a machine learning model that did really, really good on just the data that we trained it on, but then if we apply it to some other data, it does terribly. So we hold back some of the training data that we have to test our model on at the end, to make sure that it works more generally. This is from that testing sample. So this is the data that we use that the model actually hasn't seen before, so that we can feel much more confident that it's learned something which is generally okay. But it was trained to translate between images which look like these, pairs of images of low resolution and high resolution data. Sweet. But I hope you'll agree that our output looks a hell of a lot better than the input. It looks much more like that high resolution simulation. But because our machine learning algorithm is really, really fast, we effectively save an order of 1,000 in computational cost. It's 1,000 times as expensive to run the high resolution simulation than it is to run the low resolution simulation. And our machine learning model just runs like that. So it's effectively, we've created a simulation which is almost as good for 1/1,000 the cost. But looking at these pictures is only part of the story, because we want to know statistically, does our machine learning model do better? We could fool our eyes, but we can't fool the statistics. Let's see how those look. These are two statistical metrics of space. This one over here is telling you how much of each region of space is either totally in shadow or totally not in shadow. And we want our machine learning model to reproduce something which looks as close as we can to this white dotted line, but the low resolution input is the orange line. So you can notice that this orange line is off by like a factor of 50% in some regions compared to the white dotted line, whereas our machine learned output, which is we've applied some kind of correction factor to the orange simulation, is within 10% error everywhere. Here's another statistic that we care about. This is called the power spectrum. It tells us it's like taking the Fourier transform in 3D. What is the amount of each kind of wavelength in space? You can imagine fluctuations in space having some kind of characteristic distance. Here's a galaxy, here's another galaxy. How common is that separation? Again, we want to be as close as we can to the white line. The orange simulation, the low resolution simulation, is off by even factors of 100% or more in certain places. Whereas our machine learned correction factor makes it better to than 10% error just about everywhere. And at least everywhere that is at a low enough resolution that we can actually see it using our surrogate telescopes. So we've done a really good job. Now we can feel numerically confident that our machine learning model is producing something which is really useful for precision cosmology. There's one final thing which is really nice, is we can estimate the uncertainty in our model's output. We don't just receive a single output and some data and then we're done. If we run our model over and over and over again, it will actually give us slightly different outputs every time. And in certain places, it'll output effectively the same number every single time we run it. And in other places, they'll vary much more wildly. And we can compare, how much the output changes in this region of space to another region of space to have some kind of metric for how certain is the model about what the value in that place should be. In other words, if it's outputting the same value every time, then it feels pretty sure that that's the correct value. But if every time we run the model, it outputs a different value, then we can say that it's not very sure about what the value should be there. So here we have the target. This is the thing that we're trying to produce compared to the output of our machine learning model. And now I'm plotting in orange the error between those two, so one minus the other. And then in purple, I'm plotting the model uncertainty, this value of how much is the output changing run to run. And you can see that these they seem to have a very similar shape. The regions which are darker in orange are also darker in purple. If the model is having much more error in certain regions, it's also being less sure about the output in that region. And we can actually correlate this in space by plotting the uncertainty versus the error. And we see that there's this very nice power law between these two. It seems like if the uncertainty is higher, the error is also likely to be higher, which helps us to do precision science. To do precision science, we need to have a metric for how uncertain we are about it. Sweet. So bringing this all together, this allows us to make simulations which are much bigger than before. This box in the dotted line here is previously the biggest simulation which we could run on our supercomputers. The big box now is what we're actually able to do using our machine learning algorithm. We can run much bigger simulations because we can do it for cheaper. Sweet. I think that I will stop there and take your questions now. So thank you all for listening. We're using the numerical simulation. So we're running a simulation with the same initial conditions and the same cosmological parameters, but at high resolution and at low resolution. And so we have a pair, low resolution versus high resolution. We can try to train our model to take in one and output the other. But this is all simulated data. Yeah.
Do you use like the knowledge you have of how galaxies form when you make a loss function?
Yeah, we can. Yes, I'll repeat the question. So the question, I'm going to just make it more general for you, sorry, is can we use our understanding of physics to inform the loss function that we train our machine learning algorithm on? And the answer is yes, we can. In particular, we can use those two statistics that we care about as well. The most naive loss function that we can come up with is just compare one image, the correct answer, to the answer output by our model, subtract them and say, okay, we want that difference to be as low as possible. That's really great, and it'll get us pretty far. We can also take into account statistical metrics, things that we know should be true about physics, and build them into our loss function. So absolutely, yes, we can do that, and we do that, and we see a lot of success, a lot of improvement when we include information like that. Great question. Great. Yeah.
If you go back to slide like 1 7, something like that, where you're showing like the function. Why are you using somebody and like that?
Oh, these are just two really like traditional things that everyone plots. There's actually a lot more parameters than just two, but these are representing like the curvature of space-time, which is very much related in our theory of general relativity to how fast it should be expanding, to the amount of matter there is. So this sigma 8 term is telling us how much is space-time curved, therefore how fast should it be expanding. And omega matter is telling us how much matter is there in the universe. And we want to find, some kind of position in phase space of our actual universe. What is the actual value of the expansion rate of the universe? And what is the actual value of what is the density of matter of the universe?
Yeah. If you so go back even more, you have a diagram with like one, two, three, like universe.
The diagram? Oh, in the very beginning. Yeah.
Like, if you toggle for how long the push period is, or
Right. Okay, let me repeat this question. So we're now talking about inflation, which is a kind of even more specific theory of cosmology, which holds that in the very first moment after the Big Bang, the universe expanded really, really, really fast. So nowadays it's expanding at a kind of leisurely pace, still pretty quickly. But this theory of inflation holds that in the very first instant after the Big Bang, the universe expanded very, very, very quickly. Fortunately for us, that's before the CMB. So the CMB is the cosmic microwave background is this light which is emitted once the universe gets cold enough, big enough that it's no longer a plasma, and so light can travel through the universe now. If the universe is a plasma, any light which is emitted is then immediately reabsorbed by some free electron. But once the universe becomes big enough that it's no longer everything is so dense that it's a plasma, light can travel through the universe. The echo of that moment, light from that critical instant where the universe stops being a plasma and becomes a gas, is still traveling through the universe right now. We can observe it using our radio telescopes. This is what the sun is. The cosmic microwave background, that critical moment happens after inflation. So it doesn't actually matter what exactly happens during inflation because we have this snapshot already from after that moment, and we can start our simulations from then and look afterward. There's all kinds of questions you could ask about how do we simulate inflation? Can we make some kind of assumptions about quantum fluctuations in the very beginning of the universe and then expand them outwards to reproduce the CMB? But this is an entirely different project. Good questions. Yeah.
Well, the advice would you give for people who are trying to get research that are
Right.
involved in kind of
So this is a really good time to be interested in things like machine learning. I'm an undergrad here at Berkeley, and I'm able to contribute to projects like this, and take leadership, take ownership of this research process because the stuff that we're doing is so new. Oftentimes in physics, especially, you need to be a professor with 20 years of experience to be able to be pushing the forefront of research. Because you need tons and tons and tons of training on the work that's been done before you in order to be able to contribute yourself. But in this field of machine learning for physics, everything is so new. All of the techniques are like 1 year old, if that. The field is being overturned every 6 months or something. So all of us are on exactly the same footing as the tenured professors. And in fact, as students, I think we have a little more time on it. So there's a lot of opportunity for students like us to contribute to projects like this in such a new field like machine learning applications to physics. In my mind, the best way to get involved is to attend other people's talks. There's colloquiums that happen every week, or colloquia, I don't know. Seminars, talks, and you can go to these talks to get a picture of what is actually going on in this field of research. And once you have an idea of what people are working on, what kinds of questions are available and active in inquiry, you can form a picture of what you're interested in, what excites you as a person, and then maybe reach out to the people working on projects like that. Not all of them will respond to you. That's just kind of how the world is, but some of them might. And if you're persistent, and if you can advocate for yourself, be eager, be excited, people will love to work with you. People love to have an undergraduate student come in and say, I think that your work is awesome, and I would like to be involved in it in any way I can. Chances are someone will say yes to that. If you're interested in doing research, this is, in my opinion, the best way to go is to just sit in on those conversations that people have with their peers, these colloquia and seminars and whatever, about the work they're doing, and then reach out to them. Say, hey, I love this talk that you gave. Hey, I read this paper of yours and I thought it was awesome. How can I be involved? Because those are the people that know best. There will be these URAPs and REUs and stuff like that you write these very complicated applications to. And those are a great opportunity, and you should absolutely apply for those, but they aren't the only way to get involved with research. And if you want to have a good idea of what's going on, reading through URAP postings is not the way to go. Sweet. Other questions? Yeah.
When did you get started with research?
I started pretty early, and I ended up getting this job when I was a freshman here. Just by doing what I just told you to do, which was going to seminars. And then I saw a seminar about work like this that I thought was very interesting. And I had been doing this deep dive into what is machine learning at the time. And I basically pitched to that researcher, hey, these are really cool. This problem that you're running into about not being able to do the simulations you want to because they're so expensive. What if we could solve that problem with machine learning? And I ended up getting hired to work there that summer, and I've been working there ever since. Yeah. Other questions about this project, or more generally about how to get involved with research at Berkeley, physics, or anything else? I'm happy to talk about this kind of thing because I really do want to help all of you out in getting involved with research because it's really hard to do. Yeah.
Did you conduct all this
It's up to the Hill at Berkeley Lab. Let me give you a pitch about Berkeley Lab and why you should reach out to those people. We do have lots of really great people here on campus in this building. But you know, there's only so many of them. There's like, I don't know, a couple dozen professors and then many postdocs. But we have this state-of-the-art national lab up the hill from here. And I think there's something like 10,000 employees who work at the Berkeley Lab. And I don't know, at least a couple thousand of them work on physics research. Even a few hundred work on research in cosmology specifically. So there's tons and tons more people up there, and they do research full time. They don't spend half their time teaching or whatever. So if you haven't gotten a chance to meet people who work at Berkeley Lab or to even visit Berkeley Lab, I highly recommend it. It's a great place to work. They treat us all students very well there as well. Yeah.
So like how much students are studying when you talk about the research, like you have to like take every but when you were like trying to find a research, how did you reach out to the person to picture like you were college at the time?
Right. So the question is, you know, how much should you study? How many classes should you take before reaching out to people? And I should say that there's not one answer to this. This will depend pretty heavily on what kind of projects you're wanting to do. If you're wanting to like do theoretical research in quantum field theory, probably you have to take a lot of classes to do that. But if you want to like do field work, you want to be one of the people who's like pipetting things all day or doing experiments with your hands, you might have to take even a lot fewer classes to prepare for that. It's really, really dependent. So I don't know how to give a more precise answer than that. But you don't necessarily have to take classes to have an idea of what something is about. You know, I began this research before I took a class about cosmology. But I had spent a lot of time reading about cosmology in books and watching videos and documentaries about it. So I had had some exposure to the ideas. I had some idea of what the questions were and how the methods that we were doing were relevant towards solving this question, even though I hadn't taken the class. So it's going to really depend a lot on both the questions that you're interested in pursuing and what kind of work you've done outside of class. Class is not the only thing. Class is not the be-all, end-all of are you qualified. You can spend lots of time. And it's never been easier than it is right now to learn something on your own time on like YouTube or Khan Academy or whatever. There's tons and tons of great resources on the internet available to you for free. If you're interested and curious, you can teach something to yourself without having to wait like another 5 years to take a graduate course about it. And oftentimes that will be enough to wedge your foot in the door and begin doing research. Wait. Yeah.
Did you take the university class before you started research, like the 28 or 6, whatever?
I'm actually taking physics 188 right now. It's kind of chill for me because I know what I'm about. But I really do recommend the class. Professor Salyak is great. But I had done a lot of machine learning experimentation back when I was in high school. Or really the summer after high school, but before now, I had spent a lot of time like playing around on my own time with machine learning. So you don't have to take a class about it if you have that self-motivation to learn it and keep yourself accountable. Sweet. I know that was the bell.
Can I speak your one last time?
Yeah, it was great to meet all of you. And I hope that as budding physicists or mathematicians or chemists or whatever, I don't know who exactly the audience is, that you will all have a great experience in your pursuit of education and in your first steps into research. I thank you all again for your time.